All right, welcome everyone. So today we are talking about the second of our three methods for coming up with the distribution of a new random variable that's a function of an existing random variable. So this is known as the method of transformations. And based on what we're doing in class today, I recommend trying those three problems on homework 10 after class today. Also, if you would, please bring your laptops to class tomorrow so we can do some work in R in our activity. All right, so with the method of transformations, suppose that we're defining a new random variable u based on a function h of the random variable y. The method of transformations is valid only when h is either an increasing function or a decreasing function, but it can't do both. And this is true on the values of y, where the density function of y is positive. So for example, if we have the function u equals y squared, it would be perfectly fine to use the method of transformations if y is a uniform random variable between 0 and 2, because when y is between 0 and 2, y squared is only an increasing function. But if y was uniform on -1 to 1, then on that interval, y squared is both decreasing and increasing. So we couldn't use the method of transformations in that case. We would have to use the method of distribution functions that we talked about last week. So our steps for the method of transformations are, we're going to start by solving the function u equals h of y, solve that for y. So that gives us y is equal to h inverse of u. And this is why we require h to be either increasing or decreasing, is because we need it to have a unique inverse. Then we need to find the range of values for u. Then we take the derivative of h inverse with respect to u. And finally, the density function for u is going to equal the density function for y, but with h inverse of u plugged in for y. So h inverse of u is y, so this is just rewriting y in terms of u in the density function. And then we multiply by the absolute value of the derivative of h inverse. So the idea here is, thinking back to the method of distribution functions from last week, we were integrating the density function for y to find the distribution function, big F of u, and then we were taking the derivative to find little f of u. So the method of transformations is all about the idea of, well, taking the integral and then taking the derivative is kind of redundant. Maybe we can simplify that if h is invertible. In that case, we have a shortcut. So in that case, we know that the density function of u is going to be the derivative of the distribution function of u, which is going to be the derivative of big F of y with h inverse of u plugged in. So taking the derivative of big F of y, we get little f of y, the density function of y. But then using the chain rule, we need to multiply by the derivative of the inside. So that's where this derivative of h inverse comes from. That's from the chain rule. And we use the absolute value of the derivative there because we know that the density function needs to be positive, not negative. Questions about this overview? All right. So let's try this with this problem that we looked at last Thursday. So we're going to let little f of y be 2y for y between 0 and 1. And we'll let u equal 3y minus 1. So first of all, step 0 is to decide whether we can use the method of transformations. And to decide that, we want to look at the function that u is of y. So again, we're ignoring the density function. We don't use the 2y at all. We're using the 3y minus 1. Well, that's an increasing function. It's a linear function of y. So that means that, yes, we'll be able to find its inverse. So step 1, we're going to solve this u equals h of y for y. So we have u equal to 3y minus 1. So we can add 1 to both sides and then divide both sides by 3. So we get y equals u plus 1 all over 3. So this u plus 1 over 3 is our h inverse of u. Sorry, that should be h inverse of u. All right, so then step 2, we want the range of values for u. So we can start with our range of values for y, that y is between 0 and 1. And now we know that y equals u plus 1 over 3. So we can replace y with u plus 1 over 3. And then we want to solve this inequality to get u by itself. So multiply everything by 3, and then subtract 1 from everything. So we get u needs to be between -1 and 2. So that's the same range of possible values for u that we got on Thursday. But on Thursday, we got it by graphing. This time we got it by using H inverse. All right. So then step 3, we're going to take the derivative of H inverse. So we're taking the derivative of u plus 1 over 3. So the derivative of u over 3 is 1/3. Derivative of 1 over 3 is 0. So we just have 1/3. And finally, we'll use our formula. So we're going to take the density function for y, which was 2y, and we're going to plug in for y what y equaled, which was u plus 1 over 3. And then we're going to multiply by the derivative, the absolute value of the derivative that we found in step 3. So we're going to multiply by 1/3. So we get 2 times y, which is now u plus 1 over 3, times the absolute value of 1/3. And we can simplify that into 2 over 9 times the quantity u plus 1. And that's valid for values of u between -1 and 2. And if you look back in your notes, you'll see that that's the same formula as we got using the method of distribution functions. We just got it in a different way. Questions about this process? Folks online, any questions? All right. So now let's try it with the same density function, f of y equals 2y, for y between 0 and 1. But this time we'll let u equal -4y plus 3. So first of all, can we use the method of transformations here? Yeah, Sam, how do we know we can use the method of transformations? Yeah, it's just a linear decreasing function for all the values of y that we're interested in. All right. So try using that first step. Find H inverse of u. All right. So we start with u is equal to -4y plus 3, and then we want to solve that for y. So we can subtract 3 from both sides, and then divide both sides by -4. So we get y equals u minus 3 all over -4. So that's going to be our H inverse of u. All right, for step 2, we want to find the range of values for u. So remember that the way to do this is to take your h inverse of u, the thing that's equal to y, and plug that in place of y in our range of values for y. Give that a try. Kyle.
Why do you find the range of values?
Because that's the range of values on which the density function formula works. Everything outside that range of values, the density function equals 0.
Okay.
All right, so here we have 3 minus u over, sorry, oh, right, I inverted it. Over 4 is between 0 and 1. So 3 minus u is between 0 and 4. So negative u is between negative 3 and 1. And then remember that when we multiply an inequality by a negative number, we invert the direction of the inequalities. So we get that positive u is between negative 1 and 3. All right, so third, we want to take the derivative of h inverse. So we're taking the derivative of 3 minus u over 4, and that gives us negative 1/4. So try using this to write the density function for u. All right, so we're going to take our density function for y, 2y, and plug in what y equals in terms of u. So we've got 2 times the quantity 3 minus u over 4. And then we're multiplying by the absolute value of the negative 1/4, the derivative that we found in step 3. So that's going to simplify to 3 minus u over 2 times positive 1/4, or 3 minus u over 8 for u between negative 1 and 3. Questions about this? All right. So let's take a look at a more complicated case, which is when u is a function of 2 random variables, say x and y. So for example, suppose that the density function for x and y is e to the negative quantity x plus y, for x and y both greater than 0. And let's let u equal x plus y. So our strategy here is going to be to hold one of the random variables constant. Say x equals the constant a. And then we'll use the method of transformations to find the joint density of x and u. And then we'll integrate that to find the marginal density of just U by itself. All right. So let's start by letting x equal some constant a that we know is going to be greater than or equal to 0, because that was one of our restrictions on our density function. So then our function for u becomes u equals a plus y. So now we're thinking about this as a function of just y. So now we can use the method of transformations. So our h function is u equals a plus y. And we want to solve that for y. So we get y is equal to u minus a as our h inverse of u. Then our restrictions on the bounds of y were that y had to be greater than or equal to 0. So that means that u minus a has to be greater than or equal to 0. So if we add a to both sides here, we get that u must be greater than or equal to a. All right. So next we want to take the derivative of h inverse. Whoops, we need a derivative in here. So the derivative of h inverse of u is just the derivative of u minus a. And remember that a is a constant, so we're taking the derivative with respect to u. So the derivative of u is just 1. So then our joint density function, little f of x and u, is going to be the joint density of x and y, where we're plugging in a for x and plugging in h inverse of u in for y. And then we're multiplying by the derivative of h inverse, absolute value of that derivative. So then our joint density function for x and y was e to the negative quantity x plus y. So we're plugging in a for x, and we're plugging in u minus a for y. So we have e to the negative a plus u minus a times the absolute value of the derivative of h inverse was just 1. So that simplifies to the joint density of x and u is e to the negative u for u greater than or equal to a. Questions so far? All right, so currently we still have a as a constant put in for x. So to get the joint density of x as a random variable with u, we need to replace the a's with x's. So we get that the joint density of x and u is e to the negative u for 0 less than or equal to x less than or equal to u. And finally, now to find the marginal density of just u, we want to take the integral of the joint density of u and x over all possible values of x. And x had 0 as a lower bound, and that was given to us initially in the problem. And we had the restriction that u was greater than or equal to x. So that means that the upper bound for x is u. So here we have the integral of e to the negative u, but it's an integral with respect to x. So the e to the negative u is just a constant as far as x is concerned. So we get x times e to the negative u, which we then evaluate at u and 0 for x. So that's going to simplify to u times e to the negative u for u greater than or equal to 0. Questions about that? Folks online, any questions? Nope. All right. So let's try this for this problem. So the joint density of x and y equals 2 times the quantity 1 minus x for x and y between 0 and 1. And this time we'll let u equal x times y. So go ahead and start by replacing x with a constant and then finding h inverse of u. So if we let x equal a, then we have u equals a times y. And then solving that for y, we get y equals u over a is our H inverse. So now go ahead and find the range of values for u. So here we had that y was between 0 and 1. So replace y by u over a. And then we want to solve that so that u is by itself. So we can multiply everything in this inequality by a. So we get that u is between 0 and a. All right, what's our next step going to be? Take the derivative. So we want the derivative of H inverse of u. So in other words, the derivative of u over a with respect to u, treating a as a constant. So what's that going to be?
1 over.
1 over a. Excellent. And as a note, we had that x was between 0 and 1. So that means a is between 0 and 1. So we know that this is already positive. So when we go to take the absolute value, we're just going to get 1 over a. All right. So finally, we want to put this together into the formula for the joint density of x and u. Give that a try. All right. So our joint density of x and y was 2 times 1 minus x. So we have 2 times 1 minus a. So here there weren't any y's that we needed to replace with u over a. And then we're multiplying by the absolute value of the derivative of H inverse, which was 1 over a. And this is valid for a, or x, between 0 and 1, and u between 0 and a, which was what we found on the last slide for the range of values for u. All right, let's see. So as we said, 1 over a is going to be positive, so we don't need those absolute value bars in there anymore. And we can simplify our range of values for u and a as saying that u is between 0 and a is less than or equal to 1. So try writing out the integral that you would use to find the marginal density of just u. right. So we're replacing the a's with x's. So we have 2 times the quantity 1 minus x times 1 over x. We're taking the integral with respect to x, so the other variable, because we want the marginal density function for u. And then our bounds of integration are the possible values of x. So those are going to be from u up to 1. And when you do this integral, so we can start by multiplying the 1 over x inside the parentheses. And then take the antiderivative, we get 2 times the quantity natural log of x minus x. And we're evaluating that at u and at 1. So when we plug in 1, the natural log of 1 is 0, so 0 minus 1. When we plug in u, we get the natural log of u minus u. So that simplifies to 2 times the quantity u minus 1 minus the natural log of u for u between 0 and 1. Any questions about this? Sam?
Doesn't u go from 0 to x?
Yes, it did. But now once we've taken the marginal density of u, we've integrated out across the possible values of x. So we no longer care about the value of x. This is just now ignoring x because we've summed over its possible values.
Okay. So how do we know u goes from 0 to 1 then?
So yeah, good question. Going back to our range of possible values for u and x, we had 0 less than or equal to u, less than or equal to a, less than or equal to 1. So if you sort of just cross out the a here, you end up with u is between 0 and 1.
Okay.
Other questions about this example? All right. So here's an example that we've looked at before to find the expected value of the profit. Now let's find the distribution. So y, the proportion of time that a machine is down for repairs, has a beta distribution with alpha equal to 1 and beta equal to 2. And the daily profits are 200 minus 100y squared. And we want to find the distribution of the profit. So first question, can we use the method of transformations here? Kyle, what do you think?
You cannot be labeled domain for y.
So what is the domain for y?
Would it be 1 to 2?
No. Remember that a beta distribution is often used to represent a proportion. So, Sam?
So 0 to 1?
Yeah, so a beta distribution has possible values of y between 0 and 1. And it doesn't matter what alpha and beta are, it's the same range. So because y is always positive here, y squared is always increasing, which means that 200 minus 100y squared is always decreasing. So we are okay to use the method of transformations, even though we have a y squared in our formula for the profit. So try using the method of transformations to find the distribution of the profit. All right, so there's our graph of u as a function of y. We can see it's decreasing. And we can also use that to find the range of values for u, to say that u is between 100 and 200. So then our function h is u equals h of y, u equals 200 minus 100y squared. So then h inverse is we want to solve this for y. So 100y squared equals 200 minus u. So y squared equals 2 minus u over 100. So y equals either plus or minus the square root of 2 minus u over 100. Do we want the positive or the negative square root in this case? Kyle?
Positive,
Yeah, how come?
because all the y values are positive.
Yeah, by looking at the range of possible values for y, y had to be between 0 and 1. So that means we want the positive square root. So our h inverse of u is the positive square root of 2 minus u over 100. All right, we already found the range of values for u by looking at the graph. So we can skip to step 3. So the derivative of h inverse is, using the power rule, 1/2 times 2 minus u over 100 to the negative 1/2 times the derivative of the inside, so chain rule, so times negative 1 over 100. So then putting it all together, we had that y had a beta distribution with alpha equal to 1 and beta equal to 2. So we know the density function for y. And notice that now step 4 is the first time we're actually using the density function for y. Before, all we were using was the range of possible values for y. All right, so here's what that looks like, plugging in h inverse for y to get that in terms of u, and plugging in our derivative of h inverse. Remember that gamma of a positive integer is the factorial of that integer minus 1. So we have 2 factorial over 0 factorial times 1 factorial. And we can simplify all of that to end up with our density function, 1 over 100 times the quantity 1 over the square root of 2 minus u over 100 minus 1 for u between 100 and 200. Any questions about this? All right, we are about out of time, so we will finish up with this example tomorrow as we see how to use this to find expected values. And then we'll do some more practice with the method of transformations. I'll see you then.